Hi friends, welcome to RLC. In this session, let's understand frequency domain sampling. For that, let's consider a signal. Let x of t be a continuous time signal. The Fourier transform ft, the Fourier transform of continuous time signal x of t is given by x of omega. Here this is a lowercase omega. X of omega is equal to integral t tending from negative infinity to positive infinity x of t into e power minus j omega t into dt, where omega, the lowercase omega here, is a time domain variable, and unit is radians per second. Unit is radians per second. Next, the Fourier transform of a discrete time signal, say x of n, let x of n be the discrete time signal. The Fourier transform of discrete time signal x of n is given by x of omega. Here this is uppercase omega is equal to summation n tending from minus infinity to plus infinity x of n into e power minus j omega n. Here omega is a frequency domain variable, and the unit is radians. Here in frequency domain, and this omega is a frequency domain variable. X of omega is called as spectrum. What spectrum? It is the Fourier spectrum. Of x of n, discrete signal x of n. Why we are considering Fourier transform? Because Fourier transform is one of the important tool to analyze the frequency content of the signals. All the signals in nature are analog. Analog signals are converted to discrete signals. These discrete signals Fourier transform gives the frequency content. It is one of the important tool to analyze the frequency content of the signals. So Fourier transform is considered. Now we have the Fourier transform of a discrete time signal given by x of omega is equal to summation n ranging from negative infinity to positive infinity x of n into e power minus j omega n. Omega is a frequency domain variable, and omega is the fundamental frequency. It is the fundamental frequency with fundamental frequency period of 0 to 2 pi. Now let's consider a signal in frequency domain. Let's have a signal in frequency domain, that is x of omega is the signal, and x-axis is omega, the fundamental frequency variable. Let the signal of this shape. Now let this be a aperiodic signal, that is a non-periodic signal, and let me consider the fundamental frequency period. This is 0, this is 1 fundamental frequency range, 2 pi. Similarly on the left hand side, let this be on the left hand side, this will be minus 2 pi. Now let's sample this signal. This is the frequency domain signal with a fundamental frequency variable omega ranging from 0 to 2 pi. Let's sample this signal. Have let me have n samples. Let n be the number of samples. Number of samples. These samples are equidistant samples. Equidistant samples. If I sample this signal with equidistant, let n be the number ranging from 0 to 2 pi with the fundamental frequency ranging from 0 to 2 pi. Within this range, let me sample the signal. Say at 0, starting from 0, let this be at omega is equal to 0th sample. Next at omega is equal to 1 sample. Omega is equal to 2. Omega is equal to 3, 4, so on up to the last sample. In one fundamental frequency, the last sample value will be here n minus 1. N minus 1. Starting from 0, have sampled equidistant samples, considering equidistant samples up to n minus 1. If I start from 0, the last sample will be n minus 1. Then the total number of samples will be n. If I start numbering from 1, then the last sample will be n. The total number of samples will be n. So to get n samples, if I start from number 0, the last sample will be n minus 1. If I start from 1, the last sample will be n. Now, this samples, whatever we have sampled in frequency domain, that representation of the signals, let me represent those signals. Only the sampled signals, x-axis will be n and y-axis will be x of n. The discrete samples or the sequences, we get the sequences. I'll represent those sequences for one time period. This is 0, n is equal to 0th sample, then n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, so on. The last sample is n minus 1th sample. The last sample is n minus 1 sample. N minus 1 sample. In one fundamental frequency period, observe the n is ranging from n is equal to 0 to n minus 1. Total number of samples, the total number of samples will be n. Total number of samples will be n. All the samples are equidistantly spaced. All the samples are equidistantly spaced. This is the sequences. What do we get? This is sequence representation. Discrete sequence representation. This is a discrete sampled sequence in frequency domain, that is frequency domain sampled sequence having n number of samples, ranging from 0 to n minus 1. Now let the distance between each sample be delta omega. Delta omega is the distance between the samples given by delta omega is equal to the total time period is 2 pi by number of samples is n. So the distance between each sample is 2 pi by n. All the samples are equidistant. All the samples are equidistant. This is equidistant sampling space. Equidistant sampling space here, which is equal to 2 pi by n. So omega, the frequency domain variable, can be represented as 2 pi by n into k. Now this represents the number of samples. We have divided omega into 2 pi by n into k number of samples, where the range of k is between 0 to n minus 1. Say if k is equal to 0, omega is 0, which represents the value at 0, the distance is 0. At k is equal to 1, omega is equal to 2 pi by n. 2 pi by n represents the distance from 0 to 1. Sampling distance from the 0th sample to 1 sample. So if k is equal to 2, omega value is 4 pi by n. 4 pi by n represents the distance from 0th sample to second sample, and so on. We have the Fourier transform of a discrete time signal given by x of omega is equal to summation n tending from negative infinity to positive infinity x of n into e power minus j omega n, where omega value is given by 2 pi by n into k. So substitute the value here. X of 2 pi by n into k is equal to summation n ranging from negative infinity to positive infinity x of n into e power minus j 2 pi by n into k, which is the omega value into n. Now the x of n in this right hand side consists of infinite number of summations. X of n is having infinite number of summations. N ranging from negative infinity to positive infinity. X of n consists of infinite number of summations. So we need to expand this. In this expression here, x of n consists of infinite number of summations. Say this as equation 1. If we expand this summation x of n, if we expand x of n, which consists of infinite number of summation, each summation will consist of n samples. Each summation consists of n samples. Say if n is ranging from 0 to n minus 1, if n ranges from 0 to n minus 1, we get n samples. Say if n is starting from capital N, then we get 2n minus 1, the upper range. Again we'll be having n samples. That is, add n to this expression. 0 plus n will become capital N to 2n minus 1. Total again n number of samples. Again if n is starting from minus n, we get up to minus 1. Again we'll be having n samples. So on. Now expanding the expression, equation 1. Expanding equation 1, we get x of 2 pi by n into k will be equal to summation. If I start from negative n, we get minus n to minus 1 x of n into e power minus j 2 pi k n by n. Left hand side there will be so many summations, because from minus infinity to plus infinity, plus summation n is equal to 0 to n minus 1 x of n into e power minus j 2 pi k n by n plus summation n is equal to capital N to 2n minus 1 x of n into e power minus j 2 pi k n by n plus so on. Minus infinity to plus infinity, it consists of infinite number of summations. Say I'll consider this as equation 2. Let this be equation 2. Now equation 2 can be represented in a compact manner, that is x of 2 pi by n into k, the left hand side, is equal to summation L tending from minus infinity to plus infinity. This is the outer summation. Inner summation is summation n is equal to L into n to ln plus n minus 1 x of n into e power minus j 2 pi kn by n. Now consider the inner summation here. In the inner summation, if I put L is equal to 0, then n ranges from 0 to n minus 1. We will get n samples. If I put L is equal to 1, then n ranges from n is equal to n capital N to 2n minus 1. Again we will be having n number of samples. If I put L is equal to minus 1, small n is ranging from n is equal to minus n to minus 1. So equation 2 can be represented as this. So let me consider this as equation 3. Equation 3. Now say if the sequence is a periodic sequence. If the sequence is a periodic sequence, say I'll put n is equal to n minus ln. Why this substitution? Because if the sequence is periodic, it should satisfy this equation. X of n will be equal to x of n plus or minus l into n. It should satisfy the periodicity property of a periodic sequence. Even if the sequence is periodic, it should satisfy this. So this substitution is necessary here. Now if I substitute n as n minus ln, the summation changes. So the first summation is n is equal to ln. The lower range of summation we are considering in a n is equal to n. If you substitute n is equal to ln in this expression here, you will get the n range from n is equal to ln minus ln. So the n range is 0. This is the lower range. If you substitute the upper range ln plus n minus 1, that is n is equal to ln plus n minus 1, you will get here n is equal to ln plus n minus 1 minus ln. Minus ln and plus ln cancel. So the upper range is from n is equal to n minus 1. The upper range is from n is equal to n minus 1. So we get equation 3 can be written as x of 2 pi by n into k is equal to summation, outer summation, L is equal to minus infinity to plus infinity, x of n is replaced by n minus ln into, okay, before that inner summation is range. Now inner summation is ranging from summation n is equal to 0 to n minus 1. That is what this range, n is equal to 0 to n minus 1 and n is equal to 0. I have substituted n is equal to n minus ln. So it is x of n minus ln into e power minus j 2 pi k n by n. N is substituted as n minus ln. I'll get back e power minus j 2 pi k n by n. Continuing, in this expression, let's change the order of summation. By changing the order of summation, the equation can be rewritten as x of 2 pi by n into k is equal to summation n is equal to 0 to n minus 1 into summation L is equal to minus infinity to plus infinity x of n minus ln into e power minus j 2 pi by n into kn. Let this be equation number 4. Now the inner summation, that is summation L is equal to minus infinity to infinity x of n minus ln. This is nothing but the expression of a periodic sequence. If xp of n is a periodic sequence, then xp of n can be written as summation L is equal to minus infinity to plus infinity x of n minus ln. Using this expression, equation 4 can be written as x of 2 pi by n into k is equal to summation n is equal to 0 to n minus 1 xp of n into e power minus j 2 pi k n by n. Let this be equation number 5, where n is ranging from 0 to n minus 1 with n number of samples. N is ranging from 0 to n minus 1. Now xp of n is a periodic sequence. It can be written as x of n is equal to xp of n, where xp of n is a periodic sequence where the sequence repeats itself after every fundamental time period, and the n range is between 0 to n minus 1, and the value of x of n is 0 otherwise, if it is not a periodic sequence. So the equation number 5 can be written as x of 2 pi by n into k is equal to summation n is equal to 0 to n minus 1 x of n. Xp of n can be written as x of n into e power minus j 2 pi k n by n. This expression is called as discrete Fourier transform. This is called as discrete Fourier transform equation. Where a frequency domain signal is sampled into equidistant spaces, and we obtain a discrete Fourier transform of x of n, that is DFT of x of n, where x of n is a discrete time signal. We get these discrete samples from a frequency domain signal. This value is nothing but x of 2 pi by n into k. Discrete Fourier transform of x of n is nothing but x of 2 pi by n into k. Now consider equation 5. In equation 5 there is a term xp of n, which is the periodic sequence. Using Fourier series, xp of n can be represented as any periodic sequence can be represented as xp of n is equal to summation k tending from 0 to n minus 1 ak into e power j 2 pi k n by n. Let this be equation number 6, where ak is the Fourier coefficient, is called as Fourier coefficient of periodic sequence xp of n, and it is given by ak is equal to 1 over n summation n is equal to 0 to n minus 1 xp of n into e power minus j 2 pi k into n by n. Let this be equation number 7, and the k range is here between 0 to n minus 1. K is also ranging from 0 to n minus 1. Now using equation 7 and 5, observe equation 7 and 5, we can represent equation this term in summation term, summation n is equal to 0 to n minus 1 xp of n into e power minus j 2 pi k n by n as x of 2 pi by n into k using equation 5. So equation 7 can be written as ak is equal to 1 over n into x of 2 pi by n into k, where k is ranging from 0 to n minus 1, Let this be equation number 8. Substitute equation number 8 in equation number 6. Substituting equation number 8 in equation 6, we get xp of n is equal to summation k is equal to 0 to n minus 1. Ak value is 1 over n x of 2 pi by n into k into e power j 2 pi k n by n. Now xp of n is a periodic sequence, so xp of n can be written as x of n. X of n is equal to 1 over n can be taken outside, 1 by n summation k is equal to 0 to n minus 1 x of 2 pi by n into k into e power j 2 pi k n by n. This equation is called as inverse discrete Fourier transform. Inverse discrete Fourier transform. That is IDFT. It is the inverse discrete Fourier transform, IDFT. This IDFT is nothing but x of n, which is the reconstructed part of the spectrum. X of n is the reconstructed part. It is the reconstructed signal. Reconstructed signal from Fourier spectrum. Fourier spectrum Hi guys, if you have enjoyed the learning, please like and subscribe to our channel and share to your all friends and well-wishers. For regular updates, connect us on social media. Thank you for watching the video. In the next video session, let's learn about the DFT as a linear transformation.